right, now it's on. Okay, so yesterday we talked about errors and uncertainties. I believe we stopped here when Chloe solved this problem, give us the final answer of 45 plus minus 2, right? Okay, so basically when reporting results, values calculated with calculator must be rounded, right? What is the rule? First of all, the absolute uncertainty at the end that you calculate should only have one significant figure. But there is an exception. What is that exception? When the leading number is 1, then you can have 2 significant number, okay? But your precision, your decimal places should not be more precise than your original data. So if saving 2 significant figure will violate this rule, then you still need to save only 1 significant figure. Does that make sense? Okay, so that's a quick sum up from yesterday's class. Now let's move on. So let's look more into how do we deal with this when in a scenario where we're literally doing a lab and collecting data, and how do we process those data? How do we analyze them? What are the things to focus on your physics IA? Okay, so first of all, for this example, we use an extended length of the spring under the same tension and recorded 5 times, right? So what is the range and uncertainty of the repeated data here, A.0? First of all, what's the range of this set of data? (0.5). How do we calculate range? We use maximum of the data, which is 11.5, minus the minimum, which is 11.0, so we get 0.5 of the range. What about the uncertainty, Alice?
0.5 divided by 2, which is 0.25.
Very good. 0.25 is the uncertainty, half of the range. But how do we properly express the mean and uncertainty? We have the mean 11.16, and we have the uncertainty of 0.25. So we should report it as 11.16 plus minus 0.25. Is that correct?
No.
Why?
Because uncertainty is not 1, it's 2,
Okay, so first of all, 0.25 has 2 significant figures, right? We should round it up to 0.3. And second of all, our original data has only the precision to the 10th place, right? If you use 11.16, it's more accurate than your original data. That's not gonna happen. So in the end, what should be the final answer that we should report to? 11.2 plus minus 0.3. Very good. 11.2 plus minus 0.3 centimeter. Okay? So our raw data has only 1 decimal places, so our mean and uncertainty must match. In the meantime, our uncertainty should only have 1 significant figure in this case. Okay? Okay, very good. Alright, what's wrong with this one here? Why is it incorrect? So the precision, the level of preciseness does not match, right? This one has 2 decimal places, but this one only have 1. That doesn't match. And second of all, 0.36 should be reported as 0.4. Okay. Then why is this one wrong? It has one significant figure. Still, the level of preciseness does not match, right? This one is precise to the 100th place. This one only precise to the 10th place. We're not going to do this example because I believe you guys have already know how to convert absolute uncertainty into fractional and percentage, right? Do we need to repeat that? No? Very good. So Here though, let's look at this. This is a digital or analog device. Digital device because it directly gives you digits in readings, right? Readings in digits. So how do we find the uncertainty of that? Smallest increment, which is here. So if we report this reading, it should be 0.385 plus minus 0.001. 0.001. Okay, very good. 窗户都关上了，是吧？Okay. All right, propagating uncertainty through calculation. Without anything on PPT, let me ask you like a quick quiz. Mingy, so let's say y equal to a plus b, and a has an uncertainty of delta a, b has an uncertainty of delta b. What is y's uncertainty? Delta y should equal to
What's
y equal to a plus b. What is y's uncertainty when a has uncertainty of delta a and b has uncertainty of delta b? Not sure? Okay, Marvin? Let me write it down if you guys find it confusing. Y equal to a plus b, right? A has uncertainty of delta A, B has uncertainty of delta B. What is y's uncertainty? Delta y should be equal to delta A plus delta B. What if it's minus? Delta y equal to delta A minus delta B, right?
Wrong.
Can you decrease the uncertainty?
No.
Each operation you do would only make the data less and less uncertain, right? The more operation you do, the less precise or the less accurate it will be. So there's never minus or divide through uncertainty, only plus. So no matter if it's plus or minus, uncertainty always plus. That's addition and subtraction. What about multiplication and division? Let's say y equal to a times b over c. A has a uncertainty of delta A, B has a uncertainty of delta B, and C has uncertainty of delta C. Darren, what should be y's uncertainty? What's the rules for multiplication and division? Pardon me? Okay, so tell me. I'll write whatever you say.
Delta C over C.
Okay, delta C over C. Delta B over B. Delta A over A. What do we do with them? They're equal? Delta A over A equal to delta B over B equal to delta C over C? You're not sure? Add? Okay, sure. Let's add them up. And? So delta y equal to all those things passed together. Over y. Over y. Very good. The fractional uncertainty. So the key is, for multiplication and division, we do not directly plus their absolute uncertainty. We plus their fractional uncertainty. So the fractional uncertainty of y equal to the fractional uncertainty of A plus the fractional uncertainty of B plus the fractional uncertainty of C. For uncertainty, we always plus. Okay, there's no minus, there's no multiplication, always plus. It's just what to plus. For plus minus, we directly plus the absolute uncertainty. For multiplication and division, we plus the fractional uncertainty to get the fractional uncertainty of y. What if we, let's say the third situation, let's say y is equal to a to the power of n. Then what's the how can we solve the uncertainty of y when we know the uncertainty of a? Let's see. Absolute?
N times delta A over.
If here is delta a over a, that's fractional uncertainty, then
Delta Y over Y.
delta y over y. If this is fractional uncertainty, this part should also be fractional uncertainty, right? So we don't care to the power of how much. It could be 1, 2, 3, 4, even 1 over 2, 1 over 3, or negative 2, negative 3. Whatever n is, we just drag it down and put it here and absolute it. Okay? Any questions? Those are something you have already met in your A.0 math summer homework, right? If you still remember. Okay, so a quick review. Knowing that, then, so you see, capital A equal to small a times small b, then the fractional uncertainty of capital A should equal to each individual's fractional uncertainty plus together. So the absolute uncertainty of A should equal to the fractional uncertainty times A itself, which is A times B. Right? Okay. Same thing, so we're not going to spend too much time here. Same. Okay, but what about pi? What do we do with pi if we wanted to find the uncertainty of V? So let's say this equation, we're trying to find volume. Volume is area times h, right? Okay, how do we calculate area? Pi r squared, right? So pi r squared times h. We know that h, because we use ruler to measure the height, so there's going to be absolute uncertainty for h, which is delta h. We use devices to measure the radius, right? So there's going to be absolute uncertainty for that as well. We wanted to find the absolute uncertainty for delta v. How can we find? First question, does pi have an uncertainty?
No,
Why?
because it's a constant.
Pi is a constant. It's a fixed number. It's a known certain number. It's a constant. So there's no uncertainty for pi. Okay? There's no uncertainty for pi. Just ignore pi when you're finding the uncertainty. Because it doesn't have any uncertainty. It does not contribute to the overall. It won't have any effect on the overall uncertainty on the volume. Does that make sense? Okay, so then how do we find this? First of all, should we directly, what should we do with? Should we directly use absolute uncertainty? What should we use? Fractional. So let's convert that into fractional first. And then, what do we do?
It's all
Look
squared.
at the formula.
It's all squared.
So r is to the power of 2. What should we do with delta r over r?
So
Times 2. Anything else that we should do?
plus
Add them together and then equal. So how can we find the absolute uncertainty of delta v? You first of all calculate this part, and then you times v to get delta v. Okay? Any questions? Cool? Okay, good. So let's move Oh, by the way, don't round it in any of the intermediate steps. Save the value in your calculator. And then write the final answer, and then do the rounding only at the last step. Because if each step you round it, then the error is going to be greater and greater and greater. Does that make sense? Only round it at the final step. I'm not going to do the thing here, but that thing. Notice that 1 milliliter is the absolute error uncertainty, and the 1 millimeter here is also the precision. Okay? All right. So more practice question. Let's just skip. Right. Now, after we know how to propagate uncertainty, how do we deal with them? Let's see how we can actually utilize those techniques when we are having data in real IA. So in this example, a student measured the period of simple pendulum of a given length. A given length, which means the length is a constant, so it's a controlled variable, right? And record the observation in the table. Control variables can be included outside the table, which means the length can be included outside of the table. It doesn't have to include it in the table. As seen from the table showing an example of properly present raw and process the data table, which it adds a line of under the table. It says an example of proper present raw and presented data with pendulum length L brackets units centimeter equal to 80.0 plus minus 0.1. So the uncertainty of the length is 0.1 centimeter, and the best estimate or the measurements to the pendulum length is 80.0 centimeter. Okay, now let's see. We're measuring time for 10 periods. Let's look at those overall here. First of all, we have 5 sets of data. Those are the raw data, because when you're measuring the pendulum, or you're trying to measure the period, if you just measure one period, then the random error or the uncertainty could be large, right? But if you measure 10 swings in total and then divide by 10, you're reducing the uncertainty 10 times smaller. Does that make sense? Okay, so that's the reason why you see here, why is there plus minus 0.01? Like, what's the source that caused it? What's the reason? Why do you use plus minus 0.01 here? Due to the inherent uncertainty of the tool, which is the stopwatch, right? If the stopwatch can only measure like 0.52 second, then its uncertainty is plus minus 0.01 for each individual data. Alright, that's the first thing. Second thing, you are trying to find period, which is this value divided by 10, right? So 17.9, you get 1.790, right? Everything divided by 10, you get exactly here. But hold on a sec. Isn't 0.01 divided by 10 give you 0.001? Then why is it here 0.002? Why? Well, sometimes, let's think about it. Sometimes we can consider for our real life scenario, right? Is there any other possibility that can cause the uncertainty to be greater rather than this small? For example, maybe human involvement, like reaction time. So instead of really just using 0.01 divided by 10, which gives you 0.001, we believe that maybe our reaction time contributes to another certain degree of, could be more uncertain. So you can pick a uncertainty that's greater than this one. as long as you justify your reason to do so. For example, you mentioned the reaction time here. Does that make sense? Okay. Then, how do we get this mean period uncertainty of plus minus 0.0425?
Greatest and
What's the technique to get this one here?
smallest. Find greatest and smallest value.
Okay, so what's the greatest value here?
1.790.
Or 1.800? What's the smallest number here?
1.75.
Okay, what's the difference between them? 0.085. Now, what's the absolute uncertainty? Half of the range, right? So divide by 2, what you're going to get? 0.0425. Isn't it exactly this one here?
Yes.
But why is here 0.01, but here 0.0425? What are those different? Why can we directly use this one here?
Because you're using those to find.
Because that is your exact rate.
Why is this one here 0.02, this one here 0.0425? This one here, we use maximum minus minimum divided by 2. Why we use this technique to calculate this here, but not the same technique to calculate this one here?
Because you're using the average of data.
You're using the average of the data. Basically, you're processing the data. You're using the whole data, right? But this uncertainty here is the uncertainty to each single of the individual trial due to the inherent uncertainty from the tool. So the 0.002 is the uncertainty to each individual of the data. But the 0.0425 is the uncertainty of the mean data that comes from the set of this 5 data points here. That's the reason why we use different technique to use it. Okay? And we care about mean period squared. So we need to square this value to get 3.1039. Then what do we do with the uncertainty here? Do we also square this uncertainty? What do we do to find this new uncertainty? So tell me, delta T2, how do we calculate this delta T2?
Equal to delta T times 2.
Delta T2 over T2 should be equal to 2 times.
Delta T over T.
Very good. That's how you get this number. Okay? Do I explain everything clear from the start? Don't underestimate this table. Don't underestimate those numbers. It's not something you just pick randomly. It has logic in it. When you submit your IA, when you do your lab and do this data analysis, if I check your thing and it doesn't match, it's a big mistake. You're going to get a lot of points subtract from this, from the data analysis. Okay? Uncertainty is one of the most important part in your data analysis. So that's the reason why I'm going through step by step, trying to make it clear. Because a lot of students are super confused about how exactly do I find those numbers? Then they just randomly put some random number there, which unfortunately is not correct. Okay? Alright, can I move on? So, alright, so I highlighted those parts, which means, let's recall, this is due to the inheritance of the tool. And this here, why is it not 0.001? Because you need to consider other factors that might contribute to a greater uncertainty rather than just, but you need to apply your reason to justify it. Okay? How do we get this 0.425? You use a set of data, so you should use maximum minus minimum divided by 2. And how do we finally get this period square uncertainty? Use uncertainty propagation formula to get that. All the steps clear?
Yes.
Okay. So, there we go. Oh, oops. Is this correct?
Me percent.
What should we do? What should we do? Can the result be so accurate, so precise?
No.
So what should we do?
0.15.
We round it to
0.15.
0.15 or 0.2?
1.5.
1.5.
Which is one.
If it's 0.15, then what should this here be?
3.10.
3.10. Any questions? Okay, good. So, another thing is we can use our software, Excel, to show the formula, right? You can use Excel to record your data here. When using a spreadsheet, it is not always possible to include uncertainties and other details, measured quantities in the headings. But we can do, when presenting the data, any missing information can be mentioned in the text close to the screenshot of the spreadsheet data, like here. The student comments under the table, right underneath the table, saying that the length uncertainty was plus minus 0.1 for this year, and the minimum uncertainty for 10 periods was plus minus 0.01 second. Using the spreadsheet, the time for 10 periods was divided by 10, explain how to find the single one period. And then the mean value of the 5 measurements was determined to be 1.7618. And the spreadsheet was used to determine half of the range of the individual period measurements. Do I make my requirements clear? This is also IB's requirement, okay? It's from the IB's official documents. So be careful, be careful. Any questions? No, okay. Okay, here, you can also use the show formula to illustrate your data processing. So using this, then we know that you're averaging from C2 to C6. So C2 to 6, so this is the main period we know from the from the formula. And here, half of the max minus minimal, you use the max function, which will automatically find the maximal data in the range of C2 to C6, and use the main function that will give you the minimal data in the range of C2 to C6, and then times 0.5, give you half the range. Okay? Use technology. And lastly, we use D2 times D2. D2, where's D2? Here. So just average times average to get the mean square. Make sense? Okay. All right. Now, let's look at the automatic gradient determination. After we've done our data table, what's the next step to do? We need to generate the graph, right? We need to have the trend lines, right? So let's see what are the requirements. Softwares that automatically determines gradients may be used. It is allowed. However, you as a student must make clear that you understand the process of that taking place. So when you use the automatic gradient determination or generator, you should explain clearly how this works to show the examiner that you understand that you're not being lazy. You know how it works. You need to prove it explicitly. Okay? Okay. A student conducted an experiment using video to analyze the projectile motion of a ball launched horizontally from a table, most likely Logger Pro. So Logger Pro is going to be one of your best friends in DP. They're going to use Logger Pro constantly and use the linear equipment which we're going to provide you, the projectile launcher, motion detector, motion sensor, light sensor. We have a lot of those accurate equipment for you to collect your IA's to collect the data for your IA. Okay? All right. So, according to Logger Pro, we have the information of the time, information of x position, y position, and vertical speed. Okay? Now, what do we do with those data? Okay, we have this data table, so we can plug them into a graph. Now, in this graph, what we're plugging is time, velocity, or speed, time, vertical speed graph, right? Basically, you're using this column as your independent variable, and which one is your dependent variable? Vertical speed here is your dependent variable. And then you get a graph like that. So what are some details to note? First of all, legends, right? You need to name your x-axis, name your y-axis, and those scales you need to show. The trend lines, equation for the trend lines, titles of the graph. Those are the details that we're going to look at. The slope, of course, this is auto generation, but you need to show the steps here. The slope of the line is calculated as follows, right? Slope equal to delta y over delta x, which is delta y is vertical speed, so delta v over x is time, so delta t, which gives you the acceleration, in this case, calculated as 9.7804 meter per second squared. Don't forget the units. Don't forget the units. And there is no need to add the R2 value to the graph. Anybody still remember from math what is R2 value and what does it do? What does it tell us? Lucas. Forgot. Anybody?
Isn't it like how the dot is accurate to the line?
How the line is fitting your data, right? How the model is fitting your data. R2 value or R squared value here. R squared value is a number between 0 to 1. The greater it is, the closer it is to 1, it means this model fits perfectly. If it's 1, then it's perfectly fitting your data points. If it's 0, then it's not fitting at all. Alright, so here, the R2 value or R squared is a statistical measure representing the proportion of the variance in a dependent variable that is predictable from an independent variable or variable in a regression model. However, maybe your math IA requires it, but we don't need you to add the R2 value. But if you add, it's also fine. We just don't care. Okay? Alright. Now, data outliers. Sometimes when we collect data, we don't always get the, what is data outlier? Here. So when processing and graphing experimental data, there may be a data point that does not match the overall pattern or trend of other data, and that could be called as a data outlier. In this case, what is a data outlier here? Independent variable of 4. This is a data outlier here. Because it does not fit the pattern, the trend of the overall other data. Alright? So when adding the best line or best fit curve, the decision needs to be made whether to include or exclude any possible outlier. So here, does it include the data outlier? No, it does not. The best fit line does not include data outlier. Then you need to add a justification. You need to provide a justification why you include the data outlier or why you does not include the data outlier. Okay? That's why you need to provide a justification of whether you should or should not include the data outlier. Okay? Alright, so in this example, this student reasoned that this should be a linear relationship exists between the two variables, and it does not make any sense that the one point should be so far off the obvious trend. That's the reason why this student did not include the data outlier into the overall best fit line. This approach used in DP mathematics to identify outlier is not required in DP physics. Okay? You can include it, but we don't require it. Okay? Alright. Next, we have best fit line or best fit curve. This is tricky because in exam, sometimes it asks you to draw a best fit line, but the best fit line is a broad term could also mean a best fit curve. A lot of my previous students got trapped by this cap. Okay? So when you look at best fit line, don't just directly assume it's going to be a straight line. Okay? It could sometimes, it depends on the context. So you need to be careful if it's asking you to actually draw a best fit curve. Okay? This could be a trap. You need to analyze the context carefully. So a best fit line or best fit curve should be added to all graphs. All graphs. And the choice should be driven by the relevant physics theory. Which best fit line should you pick? There could be multiple lines to fit the train, but you need to have a relevant physics theory to explain it, to support your choice. Am I clear? So the best fit line or best fit curve does not need to pass through all the data points, but it at least should pass through or close to all the uncertainty bars, aka error bars. We will show you what an error bar looks like. That thing of, so this is a data point. This thing, like a 公字, this thing is what we call the error bar or the uncertainty bar. Okay? Any questions? So let's look at this one here. Would you say this best fit line is a proper one that it fits the data? So probably this is not the best choice, right? What about this one? It perfectly passed all the data points, right? Is it a good choice? Why not? It's so perfect. So perfect. Like, it literally passed through each data point. Why not?
Doesn't show like any specific trend here.
So, as you know, in math, the polynomial, is that how you call it? The polynomial term, the more term you add into it, the more precise it can fit into some certain data points. You can always construct a certain function that can pass through some certain data points. But do physics like that?
No.
We need to have a general theory that applies to all the situation, or at least under some condition, all the situation. So we do not just need a theory that can only explain one specific case. It should be applicable to similar cases. So this is actually a very bad fit line. Very, very, very bad. So no, no, no. Okay? Keep in mind, no, no, no. We don't want you to have a model that can explain perfectly, but only just this case. If anybody tells you, oh, I have this theory that can perfectly explain everything, must be a liar. Okay? However, this one is simple. It's just an exponential. We only have this to the power of something, but it also passed through the majority of the data points or with their uncertainty bar. So, would you say this is a better one? Yes. Physics likes simpleness. Okay? So, look at how complex this is. No, no. The simpler, the better. Okay? but not as simple as this. Do you get my meaning? Okay? Alright, any questions? No? Okay, good. Alright, so after we discuss about the trend line, the graph, it is time to talk about the straight line graphs. So in some cases, plotting the experimental data will generate a linear fit, which is great. Okay, 5 minutes break. Okay, 5 minutes break.